Welcome to our video on the high-speed tube-launch security UAV. This is our team. My name is Nick Hudson. We also have Landon Jecker, Nelly Mantegna, Rob Opielski, and Meg Roy. Aerial security drones are widely used around the world to collect intelligence, surveillance, and reconnaissance information. These drones vary in design to accomplish a wide range of missions. Current events in Russia's invasion of Ukraine show that designs today lack the endurance to operate a long distance away from the user while maintaining maneuverability to operate in highly congested urban environments. Therefore, there is an opportunity in the market to develop a tube-launched, man-portable, forward-swept-wing, highly maneuverable drone. We have three primary deliverables for this project. They include the completion of a full-scale mock-up, a manufacturability report, and a final report on the end state of the project. The end goal of this project was the complete design of a forward-swept-wing, tube-launched, man-portable drone that meets the range, speed, flight time, and payload requirements as set by our client. We also wanted to maximize the technology readiness level of our drone design for proposal to the U.S. Air Force. We also wanted our design to be able to be developed into an operational drone by future engineers by our client's company. Here's a high-level function overview of our drone design. We want our drone to be able to be launched from a tube, to fly, to land and be recoverable, to accommodate a payload, and to transmit and receive data. Since the goal of our project was to only create a mock-up, we focused our design mostly around the first two functions. The subsystems on our drone can be broken up into structures and mechanisms. Our structures include the fuselage, wings, canards, and rudders, and the mechanisms include the deployment mechanisms for the wings, canards, and tail, and the control surfaces such as the rudders, canard, and ailerons near the tip of each wing. For the aerodynamics of our drone, our client specified a forward-swept main wing configuration. This allows for high maneuverability with the downside of high instability. We completed multiple computational fluid dynamics simulations of our designs to analyze the flight characteristics. This includes the lift and drag. Here you can see all of our subsystems integrated together. We needed to optimize our design to reduce weight and maintain structural rigidity because there's a lot of load going through main wing and canards while the drone is maneuvering. This had to be transferred to the main fuselage without everything falling apart. Two of the requirements for our drone design were for our drone to survive a 50G tube launch and a 20G pull-up maneuver. Therefore, we performed calculations and finite elements analysis to make sure that our design would survive these maneuvers. For our control surfaces, we started by using hand calculations and then moving to computational fluid dynamics to understand the types of forces that are on them. We use this knowledge to design the control surfaces and the mechanisms that we use to actuate them. Where our main wings are mounted holds a lot of force during launch when the wings are folded, and also needs to be very rigid when the wings are fully deployed. Therefore, we took a lot of time to make sure our designs were right, and also ran multiple finite elements analysis simulations on our wing mounts. Our drone design process is not all simulation. We also need to validate our simulation with real-world testing. Therefore, we will be testing our drone design as a half-span model at the University of Buffalo Wind Tunnel. We also need to submit a manufacturability report to our client. Our drone design is going to be a proposal to the U.S. Air Force. Therefore, it needs to abide by the rules and regulations in the National Defense Authorization Act and International Traffic in Arms regulations. We also need to study how our drone could be made more easily, just in case our client gets a production contract in the future, where up to 100 per year drones would be needed. We will also submit a final report to our client that includes the background and motivation for the project, design description, feasibility evidence for our design choices, and the results, conclusions, and recommendations from our experience during the process. The future of our project includes a proposal to the U.S. Air Force with the goal of winning a developmental contract, the potential to develop a flight control system by a future student of Dr. Crucides, and the handoff of the project via Exploratory Sustainable Solutions LLC, our client, for development into an operational drone. The main challenges our team faced included integrating subsystems together for our final design, packaging constraints from having our drone be launched from a tube, minimizing the airframe weight while maximizing its strength, and construction of our prototype. Our team would like to acknowledge Dr. Crucides, who is our team mentor and client, Harold, our team guide, Cody Beal, our client, the Aero Design Club at RIT, and the University at Buffalo Mechanical Engineering Department for their help along the way in this project.